I am here to talk about fate. Does everyone believe in fate? The downside of having given this talk a couple of times is I'm running out of puns. This is one of the last ones that I have. So tonight, we're going to discuss the fact that everything happens for a reason. There's a reason everyone's here tonight, and there's a reason why we're in this room. There's a reason why I'm giving this talk. We're going to leave tonight with the belief that typed functional programming is a useful way to write JavaScript and is a useful way to write node code. Does anyone believe that now? So I've already convinced half of the audience, which is a great strike factor. All right, so I have a couple of people left to convince. So we're going to talk about a language called RESON. I'm Jacob, if anyone doesn't know me. Hi. And we're going to talk about RESON. Wow, that contrast is terrible. We're going to talk about RESON. RESON is a syntax and a toolchain for the language OCaml. Has anyone heard of OCaml before? A couple of people? Yeah, thank you. OK, so for the people who haven't heard of OCaml before, OCaml is a language from about 20 years ago. OCaml is a functional programming language, a typed functional programming language. You might be more familiar with the language Haskell. Yep. OCaml is not very much like Haskell. So the language OCaml existed for about 20 years, mostly in academia with a little bit in practice. There's a company called Jane Street in the States and in London that is one of the largest high-frequency trading houses in the world. They use OCaml internally. But short of that, there wasn't very much usage in industry until a company called Facebook came along. You might have heard of Facebook. Facebook uses OCaml a ton internally. And yeah, for anyone who hasn't heard of Facebook, they use OCaml a ton internally, and a lot of their tooling is built in OCaml. So we might be familiar with Flow, which I'll touch on in a little bit, and we might be familiar with Haxel. With HHVM, Facebook's PHP hack superset. Hack is a PHP superset written in OCaml that allows you to add very, very strong typing guarantees to PHP. But Facebook, in using all of this OCaml internally, supposedly found it quite hard to convince generic teams inside to adopt OCaml as the language that they were writing. So they found all of these big valuable properties of using types and using all of the guarantees that OCaml gives you, but they found it hard to convince people to use OCaml for a range of reasons. See, pun. But they ended up with this thought that the concepts weren't what were blocking people. It was the syntax. It was the way that the language was presented. When you have to learn something new, learning too many new things at a time is tough. So if you pick up a new language, you don't also want to learn Vim at the same time. If you pick up functional programming for the first time, it's probably not so great if you learn an entirely new syntax for doing so. So tonight, we're going to talk about using typed functional programming with V8. And I want to warn the people here that it's probably already happening for you, whether you know it or not. There are so many languages that are typed and functional that compile down to completely idiomatic JavaScript that your dependencies might already be doing this. Your toolchain might already be doing this. The framework and tooling that you use day to day might already be doing this. But I want to come out of this with a understanding that you can embrace this process, but give up none of the things that make you able to develop actual day-to-day applications with the same velocity, with the same speed, with the same comfort. But you gain all of these extra guarantees out of it. So, sorry, it's really disconcerting. My laptop is at a weird resolution, so I can see half of the screen as I'm talking about this, so I'm worried that it's cut off whenever I look at it. RESON, like I said, is a syntax for OCaml. So what that means is that the language, the underlying language, is exactly the same. RESON is OCaml. You can't do anything in OCaml you can't do in RESON. You can't do anything in RESON that you can't do in OCaml. But it's similar to how Babel enables us to write different syntaxes of JavaScript and compile them or transpile them down to valid ES5. Similarly, RESON allows us to write a different style of OCaml, but compile it down to completely valid OCaml bytecode. So we can see here that, and this is one of my favorite tricks that you get to see when you talk about typed functional programming as not necessarily a big barrier. Both of these are exactly the same program. But they're each valid in the interpreter or in the compiler that they reference. So we have a JavaScript program, which creates an object with a key value pair. And we have a RESON program that creates an object with a key value pair. Both of these, the same program, completely valid in both sets of the language. So the idea, the concept behind RESON was to create a syntax that wouldn't kind of push people away before they'd hit why the fundamentals were so interesting. So what's the reason? Puns. We're going to cover off why types are nice. We're going to cover off by a little bit of why functional programming is nice, although I'm not going to touch very heavily on that. But at its core, this is a really kind of high level, not really very deep into the language talk. And the idea behind that is I just want to give you a taste, an introduction to what you can do with this and why you might be interested. If that concept is interesting to you, please come up afterwards and talk to me. There's a lot to discuss. There's a lot more information than what I'm going to present here. With 20, 25 minutes or so, it's really hard to start from the beginning of pure JavaScript and get towards typed, functional, all that kind of stuff. So for the people who are here, who's had a runtime error? A runtime error is something that throws in, like when it's runtime code. Anyone who doesn't have their hand up, you're lying. Yeah, or exactly, or you've caused one, but you've never debugged it. JavaScript is a language where it is almost impossible not to accidentally cause runtime errors. You have to work so hard to avoid them. The other part is, who's heard of Tony Hoare? Couple of hands. So Tony Hoare, probably very unfortunately for him, because he feels the same way, is considered the inventor of null. And he considered null his billion-dollar mistake. So JavaScript is a language that has null. It has a nullary operator. In fact, it has two. It has null and undefined, and they have different semantics. So JavaScript is a language where passing values between functions or passing references between functions might give us the ability to have an object that has no meaning, no semantic meaning in the program whatsoever. And we have no real way to guard against that. We only have runtime guarantees. We can call if this value is not null, or if this value is not defined, or if this value is neither null nor defined, since they mean different things, that we can deal with that. And the last thing that I want to touch on is that unit testing. So where unit testing falls down is this idea that we trust that our system works because we have unit tests, right? Like, we all supposedly probably write tests. Does anyone not write tests in their code base? Without any shame whatsoever, I promise. No? All right. So everyone writes tests, which is good, because you should. We're in a dynamic language with weak typing guarantees. So testing is the only real way that we have to tell, is this broken? But unit testing can never tell us, is this okay? Unit testing can only tell us, these are the ways in which it can be broken, and it isn't broken in that way. But it can't tell you that there's another way that it could be broken that it is broken for. There's a whole bunch of mathematics underlying that, and I won't go into that. But the fundamental truth of the matter is that by checking after you've written something whether it runs, you can only tell that it doesn't break in the ways that you can think of it not breaking. By checking before you run it, whether or not it should run, you can tell a lot more about the way that it could possibly break. You can tell by looking at the inputs. You can tell by examining the outputs. You can tell what all of the legal values for the software that you've just written, whether or not it's okay. The fundamental idea for why we might want to add typing to a system is that it's much easier to make the states of our system that are illegal totally unrepresentable. So we've all written code that has to do either duck typing or my favorite phrase for it, which is duck punching, which is so cruel to mallards. But that is kind of a dangerous place to be. If we try and send messages to an object and assume that if it can handle it, it'll handle it, and we try and catch, and if it doesn't handle it, then we do something else. This is a dangerous place to be. Calling try catch on code where we're just assuming ahead of time something might throw an exception, we're assuming going into our programming that something is unsafe and that we can't do anything about it. This isn't a comfortable place to be. It's much nicer starting from the hard assumption that if I can get the computer to tell me that nothing has gone wrong with what I've written, that I'm fairly comfortable that nothing has gone wrong with what I'm written. I'm not very good at thinking like a compiler. I'd wager that most people aren't very good at thinking like compilers. But we've written programs that are specialized for telling us whether or not things are okay, whether or not these values are legal in the functions that we're passing them into. Rather than us trying to second guess ourselves throughout an entire program, some of which might be thousands of lines long, it's quite nice to just have something that can, in a couple of seconds, go, no, everything's fine, don't worry about it, you're all good. So touching on this concept of unit testing and the idea that we want to make things that shouldn't exist unable to exist, by using types and by using functional programming, we can actually make it so difficult to represent states that shouldn't exist in our program, because we can make the computer yell at us when something is wrong. And that always sounds kind of antagonistic. That always sounds kind of difficult. Like, I don't want to spend my day with a computer yelling at me. I don't want to feel like I'm fighting the compiler at every step of the way. But there's kind of an important semantic to take from this, which is that you can spend more time focusing on delivering value, delivering a product, delivering a feature, if you're not also spending all of your time thinking, did I pass an object that has the key A in this position? Do I have to check against the return type whether or not it has this particular property? The compiler can do all of that for you as long as you can structure your program in the right way. So it's quite a nice position to be in. So this is Express controller code that I have seen in every country that in every company that I've written Express for, well, also in every country that I've worked in. But this is Express code that I've seen in every company that I've worked in. Can everyone see what the issue with this code is? So the input type of this code takes a request object, a response object, and a next. If a condition matches, it responds with 1. If another condition matches, it responds with 2. What happens if it doesn't match either of those? Are we running Nginx? Are we using something that has a 5-second timeout? Is Express configured with a 30-second automatic timeout? We don't know. So our system is very, very vulnerable to these kind of issues in our program. We're in a position where even something as simple as just forgetting to return from a function can lead us into a position where we hang our server for 30 seconds. JavaScript is concurrent, but if you're in a synchronous program and you have a lot of these moments where it's just hanging for 30 seconds, at some point you'll hit the edge of your program's ability to continue responding to requests. And it'll just kind of check, 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 can't do anything, hangs here for 30 seconds, and then dies. So we're talking about types. And I'm going to get to RESON and OCaml and all the fun stuff in a second. But I can hear everyone saying, thinking, that there are already type systems for JavaScript. We already have Flow, we already have TypeScript. We already have a range of options. Why can't we just use those? So was anyone at the meetup event last night, listening to Ryan Kavanagh? 1, 2, a couple of people. So you would have heard a lot about TypeScript, probably a little bit about Flow, a little bit about how to add types to JavaScript programs. But for me, given my choice, I'd prefer not to use Flow and TypeScript. And there's a reason behind that. Pun again. And the underlying idea is that Flow and TypeScript are amazing. They're miracles of engineering. They give us the ability to add these things to a program with such little friction. It's actually incredible. But they're not correct. They're not sound. They give us the ability, they give us all these little escape hatches that we can go and write code that might error at runtime, and they make it easy for people to do so. Because their whole reason for existing is to make it easy for you to add type to code without any friction in the way. So as an example of that for each of them, and I'm not going to go too deep into this, this isn't intended as a negative mark against Flow and TypeScript. For what their purpose is and for what their aimed goal is, they're incredible. But let's start with Flow. Flow, which under the hood actually is written in OCaml. So in Flow, we have this ability to express these variants. Essentially, what this says is that the type A is either an object with a property T that has the value, the string A, or an object with a property T that has the type, the value, the string B, or the property T with the stripe, the type, the string C. Say the same thing 3 times. And we have a function foo because I hate naming functions. And we say that we take in an A. And we can see here we have a switch statement. So we pass in something. And if it matches the first case, then we return with the string A. Matches the second case, we return with the string B. What happens if we pass in something with the string C? We get nothing, right? So now any consumer of this function has to run a check on the response type to say, did I get back a string? If not, should I do something? But Flow doesn't warn you. It doesn't say unmatched patterns. It doesn't say, I can see that you've passed in a type A, and I can see that you've used 2 members of that type, but not a third. It doesn't warn you that anything is wrong. It gives you no tooling to help you here. It just lets you make this code. So let's look at something that RESON might do. So here we have something, an algebraic data type, an ADT, which is the type A. And the type A is either A or B or C. So the syntax for a type, and I'll go into this a little bit more later, but the syntax for a type in RESON is a lowercase name, type A, the lowercase a, and then a number of uppercase what are called constructors. These are similar to class constructors in how you can think about them. They give us a way to reference this type. And here we have 3 such constructors. We have A, B, and C, which means that we can use these to construct types anywhere in our program. So we now have a function foo, because again, I hate naming functions. And we say that foo takes a value A of type A, and it returns something of type string. And we can switch on A and tell if A is of type capital A, return the string. If A is of type capital B, return another string. I should have definitely named these nicer. A later example is better than this, I promise. But we see here another issue, right? So we can see we haven't handled C. C is something that we've said, don't really want to think about it. So what would the nice thing be for a computer to tell us at this point? We want a computer to tell us, hey, you forgot C. You should handle this. It's part of the input to your function. And indeed it does. So I'm going to introduce you to my best friend in programming at the moment, Merlin. Merlin is a program for OCaml, and because it's for OCaml, it's also for RESON. That is effectively a static analysis tool for your program. You can look over the entire program and say, here are all the things you forgot, or the things you might want to know, or here are all the completion for the properties of that function. Here are all, it's a really, really cool tool. And Merlin tells us that the pattern matching is incomplete. But it goes further than telling us that the pattern matching is incomplete. It tells us, hey, you forgot to handle C. Explicitly, in this function that you just built, you forgot this thing. The computer almost writes the program for us. It almost tells us, you should have another case after B that has C in it so that you can handle that. Let's look at TypeScript. TypeScript does, by default, something called implicit any. I'm not sure if it was mentioned last night. Did they mention no implicit any and nullable types? An infinity of silence. Okay, so it has something where if you define a function and you don't explicitly say the variables are of this type and the return is of this type, it will say internally, these can be anything. Don't restrict them to anything, don't tell them about anything, don't do anything, allow any value to be passed here, allow any value to be returned, have no type guarantee about this function whatsoever. So if we create a function foo, and we take a variable hasMethodBar, and we return the result of calling the property bar on hasMethodBar, we would expect it to return something. So we call that with an object that only has baz, and we try and call an undefined function, and it throws a runtime exception. If we call it with something that has bar, it works. But it doesn't fail at compile time. It doesn't fail when we're expecting it to tell us, hey, this should fail. We want to get out of here early so that we can fix this up earlier. So instead, we have to write unit tests now for, if I give it something that it doesn't work for, does it still catch the fact that it doesn't work for it? Or I have to write explicit type annotations for every variable for every function. In RESON, I don't have to write type variables anywhere that it can infer them. The compiler is so smart, it can tell, just looking at a function, I can see what type this is, I can see the interface of that type, and I can tell you, everywhere that you use that function, these are the things that you might want to guarantee about the variable that you've put into that function. So in this case, we define the same method foo. I think this might be the last foo in this talk. And we have a call to the variable that we've passed in. The syntax here is 2 hashes, and that's a way to access a property on an object in RESON, property on a JavaScript object specifically. And we pass in a JavaScript object that has a function that returns a string fails to compile. And we call it with that. We call foo with that, and it doesn't work. It blows up. So we can see here, Merlin, my friend again, says to us that this expression has type, we expected it of a different type, and you gave it completely the wrong type. What were you doing? So don't worry so much about the specifics there, but effectively what this is telling us is the property, the object that we passed in didn't have the property bar. Didn't help us. You passed in a property that had bars, or passed in an object that had the property bars, but we really wanted the property bar. It tells us, basically, again, writing a lot of the program for us, that if we want to use this function here, we have to add a method bar to the object, or we can't use it. So we've saved ourselves needing to write a whole series of unit tests on, is the interface of this function guaranteed? Do I need to do checks of the object that I'm passing in for duck typing? If I'm using Ruby, do I have to have method missing somewhere in the function in case it tries to call something? It saves us a lot of pain. So another aspect of where this is useful. Does everyone remember the year of JavaScript fatigue? Everyone remember when Webpack came out and Babel came out, Browserify went away and Gulp and Grunt went away, and all of the tooling that we've had to learn over the last year? Anyone think that's ended? How many tools do we use every day just to get what is effectively a dynamic scripting language to work either on the back end or the front end? So we're at Node Ninjas, so we have Node. If we're using TypeScript or Flow, we have TypeScript or Flow. If we're using anything that isn't part of the Harmony syntax at the very least, we have Babel. If we're using anything that has any kind of bundling, we have Webpack or Browserify. If we're using any kind of build tooling, we have Gulp or Grunt, or if you're super old school, Make.
It's coming back.
Oh yeah. There's actually Jake, which is JavaScript Make, because everything is going to be written in JavaScript. We have all of these tools. We have so many things to learn. We're actually, a lot of the time, more tooling engineers than we are actually software engineers. We spend more time configuring Webpack than we do writing features. So there's this concept that was raised by one of the engineers working on RESON, taming the meta language. And the idea is that all of those tools, all of the information, all of the logic that you have to learn to get to this point isn't really about the code that you're writing. Do you care if you're using Webpack? I don't. It's a great tool. I'm glad that it exists, but I don't really care about it. I don't care about Babel for all of the years of effort that have gone into it, and I'm super grateful that it exists because it saves me a hell of a lot of time. But that's not the reason why I like software. I don't like software because I get to use Babel. These are all things that exist in the ecosystem to solve problems because JavaScript fundamentally does not solve these problems for you. The language does not cater to the needs of the people who are writing the language for a living. So we have this concept of the meta language, all of the things that sit above the code that you write day to day. Wouldn't it be nice if all of that existed in the language itself so that you didn't need to learn a ton of tools every time you wanted to switch to something? Wouldn't it be nice if instead of needing a bundler, a compiler, a static analysis tool, a linter, all of these things, instead you had a very, very stripped down simple toolchain? And that's the idea behind RESON. The idea behind RESON is all of the things that we use daily in JavaScript now, in Node, in front end, across the board. These are all things that should be a first-class citizen of the language itself. And that's what the intention is to continue iterating on the toolchain and on the syntax to push these things into the language. So that all we have to think about as developers is delivering the feature in the best and safest way possible, not in learning the latest plugin for the loader for the Webpack configuration that we're using that week. And finally, the idea is that why we might want to use something like RESON over something like TypeScript or Flow. RESON is safe by default. So that's an important point, is when we're using Flow or we're using TypeScript, implicitly, if we don't type a program, if we don't add the comment at the top of a Flow file saying @flow, or if we don't set up TypeScript in order to actually say all of the types in this file are this, it might try and infer a little bit, but realistically in a Flow program, if you don't have the @flow pragma at the top, it just says everything in here is type any, by default. TypeScript has compiler options to turn off the implicit any and the nullable types options, but by default they're on. If you're consuming a project that was written in TypeScript, you almost kind of assume that typing has been done on the project somewhere. But someone can create a project with TypeScript or with Flow, say I have static analysis running, but deliver something that is typed any across the board. You don't really get any safety that way. You just get the defaults. Something like RESON actually goes the other way. By default, completely safe. It gives you the escape hatches that you might want to use. You can take off your parachute and jump out of the plane if you want to, if you think you can get to the ground safer than with a parachute. But it doesn't do that by default. It gives you a lot of safety by default. And I really like that, because I am not smart enough to trace the types through the entire program by myself. I'm just not. You can't be. So that's the idea behind all of this. I have spoken enough without showing you any real software. So let's take a look at the simplest Hello World program. Node ninjas, so we're going to focus on Express. Everyone use Express? Anyone use Happy? A couple of people. Anyone use Connect by itself? Anyone just do require http.create server? No. I really want to do that, because you actually don't lose that much. I thought you would, but there's a whole bunch that Node just gives you. But let's take a look. This is the bare bones, very, very basic Express program. So we've got const express is require express. We create an application by calling express. We create a route, a get route on slash path. We handle rec res next. We respond with a string hello world. And then we listen on port 3000. Is everyone comfortable with what this program is doing? Can anyone see a way in which this might fail? The back?
What about a different route?
Yep. So if we hit something that doesn't exist. Also, what if port 3000 isn't free? Or what if res.send fails for whatever reason?
You didn't install Express.
Or you don't have Express installed, yeah. So there are a bunch of places. No, it's a joke, yeah. That has absolutely, like your CI doesn't fire the right way, and the bundle that you build to send up as an artifact to Amazon hasn't gone quite right. Yarn has cached the wrong tar gzip package and doesn't have the file available. So there's a lot of ways that this kind of stuff can go wrong. We want to push the possibility for those things as far away from our application code as possible, right? We want to only have to think about, have I handled every route that I want to handle? Not, have I handled all of the possible ways that res might exist? Because we actually don't know what rec, res, and next are looking at this function, right? So if we have a function rec, res, next, we assume that rec, res, and next are of the types that they are, because we've all read the Express documentation probably 1,000 times, trying to find whether or not it's rec.get or rec.headers or the same kind of functions over and over again. But this doesn't give us any safety. It just gives us basically that we can go and read documentation and come back and apply that documentation to code. So instead, this is the RESON program that does exactly the same thing. It looks pretty similar, right? Like there's not really much in there. If you squint and tilt your head, this is a JavaScript program. There's not really much in there that is too different. There's a little bit of syntactic difference. So I'll run through what every step of that does. But for all intents and purposes, we use the Express module. We create an application by invoking Express. We create a route, a get route on the slash path that handles any response and calls back with the string hello world, and then listens on port 3000. It's exactly the same program for all intents and purposes, without having to think too much under the hood. So the first line, open express. Open express is kind of like const express equals require express. RESON and OCaml have this concept of a module. And a module is quite similar to what a JavaScript module is, or what a node module is. It's a way of wrapping up behavior and wrapping up data and allowing it to be consumed by other objects in the system. There are some important differences that I'm not going to go into, where they differ in their behavior or they differ in how you use them. But for this program, for all intents and purposes, if we see open variable, we're taking a module that exists somewhere and making all of the methods that exist inside that module available inside the scope that we've opened it. So if we have here the module express, and inside that module we have another module app, basically what we've done by calling open express is we've said inside the scope that I've opened this module, app is now available. You can call all of the methods that exist on app. And if I've defined anything else inside the module express, you can call all of those as well. So that's what gives us the ability to call express, which kind of looks like it's a global variable, but it's only open locally within this object. Similarly, it's what lets us call app.get, and it's what lets us call app.listen. It's a way of opening up that module and making the variables available without having to explicitly call express.app.listen every time. Similarly, maybe we go at some point, I don't like writing app.get every time. I don't like writing this way of setting up a router every time. I can see that there's a DSL, a domain-specific language, implicitly involved in setting up a web server. For what I'm designing, rather than writing that every time, maybe I set up a little mini language inside my language so that I don't have to write all of these invocations every time. So that's what we've done with route. We've said inside our program, there are 3 kinds of routes. There's an error route, which is how we handle the case if we don't supply necessarily the right route. We end up with a 404 error. We have an ordinary route, which takes a method, a string, and a middleware function. And we have a method use, or a type use. So this is the same as the syntax before, the type A, B, C syntax. And effectively, type route, which is error or route or use, is the same as saying A or B or C. It's like a logical OR. If we have a variable, if we have a function that takes a variable that is of the type route, it's either an error route or a route or use. So if we pass in anything that isn't one of those 3, it's not going to work. The compiler will fail. If we pass in something that's of those 3, but we don't give it the right data, so we try and call error route, but we give it method, string, and middleware function, compiler will fail. This gives us a really, really strong guarantee that everything that we set up for the controllers, for the routers, for the path handlers, for whatever you want to call them, very, very strong guarantee that our program is correct. So we define the allowed members, the allowed inhabitants of the type. This is the same as in this example here. We set up letters, and letters are either a capital A, a capital B, a capital C, or a capital D. And I described these before as constructors, as type constructors. And we can see a way that they can be used. We have takes a letter, take letters, and it takes a letter, which is a member of letters, and it returns a string. And for A, it returns A, and for B, it returns B, and for C, it returns C. And then we have the special underscore character. Underscore is the same as calling default. If we end up with a message passed that doesn't match any of the previous handlers for the switch case statement, it'll return whatever is matched by underscore. Underscore is the, I don't want to think about any more inhabitants for this function, just do whatever I tell you after that point. So if we call JSLog, and we call it with take letters A, it'll return A. But if we call it with take letters E, it's not going to give us the default case. It's not going to say, sure, here's whatever you get in the default. It's not going to compile, because E is not a valid inhabitor of the type letters. So this is really important as well. In JavaScript by itself, if you switch on something and you have default and you pass in something that doesn't match any of the cases you've set up, it'll hit the default. It doesn't really tell you whether your program is working correctly. It just tells you whether or not you've passed in something that matches those previous switch statements. But this is an actual compile time guarantee that nowhere in your code base do you have any code that can end up trying to pass a non-inhabitor of letters into the take letters function. So it's really safe. This is really useful. And we can use that to set up, again, a little embedded DSL for setting up a controller, for setting up a route, for setting up paths. So we create a function called extractAppMethod, and it takes a method, and it tells us which app method we should use for that. So if we pass it the constructor get, we want to use app.get. If we pass it the constructor post, we want to use app.post. And you can visualize that we can expand that out to handling put and patch and delete and any of the constructors that we might want to handle. We can pull them up into this switch method as long as we've added them into the type that handles method. But you'll also see here that I haven't explicitly typed any of these functions. I haven't said, hey, extract app method. Method is of type method that I've defined previously. You should know that. Because it can infer it. It can see that the inhabitants of that are app and post, and those are defined in the method type. So as long as that type is available in scope, it will figure out what it should use for it. Similarly, we have a method applyRoute, and applyRoute takes a server, and it takes a route. And switching on the route, it tells us if you use error route, then use app.use and pass the handler into the application. So if we want to handle an error, we call it with error route and a handler. If we want to use an ordinary route, we take a method, a path, and a handler, which are the three things that a route needs to function, and we extract the app method by using the method and pattern matching on the type of method, and we call the server and we call the path, and we pass that all through. And similarly, if we just want to use, we just use the use pattern matching. So again, this looks very, very similar to what we would do in an ordinary Express application. But we have a compile time guarantee that no part of our server is incorrect. So we don't have to write unit tests. A lot of our integration tests go away. If I call it with this route, does it handle it in the right way? If I call it with this route, does it fall through to the 404 handler? Do I get the error matching? All that kind of stuff just goes away. We have a compile time guarantee that we handle the routes in the right way, that we handle them with routes that definitely resolve, that we don't have any hanging members of our code base. And the more that you put into the type system, the more rich you define your system with types, the better your compile time guarantees are. So if you lift your effects up into the type system, if we have a difference between sending a string and sending a JSON, and we can encode that in a type, we can guarantee at compile time that this method definitely does not send JSON, that it only sends a string. If we can push up the fields on a user that we might not want to send, like password, or like all of their Stripe authentication tokens, if we can push that up into the type system, we can guarantee at compile time that we haven't accidentally given out all of our users' information out to the web for anyone who might want to see it. So the more that you can push into this, the less you actually have to pull into your unit tests. That's really the takeaway of this idea. And finally, how we actually create the application now. So we have this nice little domain-specific language. We create a list of routes. So we have a get over slash, we have a use for a error cell, and we have an error route. So the use over error cell is how we do that trick that we do in Express, where if at the very bottom of our routing tree, we haven't hit any other controllers up to this point, then we have something that basically just sets res.status is 404, because how else would you get here, and pass it on to the error handler. And then the error handler is the next thing that we call. So this is a very, very simple routing tree that we've set up. But again, compile time guarantees. We have a very, very easy way of extending this program. We have a fairly easy way of refactoring it because we know if at any point we change something and it breaks the compiler, we can chase down where it's broken and fix it. Finally, we create the app as we saw before. We iterate over the list and apply the routes to the application, and then we listen on port 3000. So this is the bread and butter of setting up a Hello World Express application. But it's not quite enough to understand how to use it with Node, right? Because so far we've just stayed inside Express. We've just stayed inside RESON code. What if we want to call out to something that exists inside JavaScript itself? You can. So I mentioned that it has ways for you to take off your parachute. And FFI is the way for you to take off your parachute and call to things that might not be typed, or might not be typed the way that you say they are. And effectively what that means is that you can write bindings inside RESON to JavaScript code, and you can say, I promise you that this function is of that type, and any way you see me use this function, treat it as if it was of that type. But it has no way to know. You could lie to it. You could say that window.document is actually a string, and it'll believe you, because it doesn't know. It doesn't know what window.document means. So this is quite dangerous. You have to be very careful when you write FFI bindings that you treat them very, very strictly, that you know exactly what they're doing. If you were going to write unit tests inside a typed functional program, FFI bindings are definitely the place that you'd want to unit test, because you have no real guarantees at compile time other than what you've said is true. So here we have something to the module fs. fs.read file is like my go-to. I use that probably in every program I've ever written in Node in some capacity. And here we have the ability to say, we have this external method read file. We're basically saying, I promise you, compiler, I promise you, there's a function read file. It's available on the module fs. So at the very tail end of that expression, we have two open square brackets and @bs module fs. What that's saying is the function that I'm setting up, the function that I'm creating, will be available on a node module fs. When you compile, you should compile to a statement that does something like require fs.read file. So the compiler takes that and does tricks with it. The compiler that I'm referencing here is called BuckleScript. It is incredible, easily the best whatever to JS compiler I've ever used. It's absolutely incredible. And it supports RESON as a first-class citizen, which is why it's one of the recommended usages for it. Just super first class. But here we have a way to say, take a string, take something that might be null or undefined, and will give us back an exception. or something that gives us a string, and we'll return an any type. So here we have an any type again, right? We have -a. And at the beginning of the talk, I was talking about how bad any types are. The difference between what are called any types or universal types or whatever in a RESON or an OCaml program versus something like Flow or TypeScript is a generic type, you can do nothing with it that needs to know about the type. So if I take in something of type '(a), I can't assume anything about that type. I can't call methods on it. I can't do anything with it explicitly, unless I type it in a certain way by saying this is of that type. So the compiler, if I give it a variable, or if I give it a method that operates on that type in a way that it cannot resolve, cannot infer, it will fail. It will say, I can't do that. I have no idea whether or not that variable should be used in that way. And it will make me add an explicit type to it. So we can use this by calling fs.readFile, and we take in a path to file. We take in UTF-8, and we basically call readFile saying it's of UTF-8, I promise you, and you can get this file at this path, and it's all fine. And we get a function back with data, and we log the data. So this is a very, very simple way to write FFI. Typed templating. So everyone use React or Angular? Anyone miss Jade? Anyone miss just like HTML as an output when building an application and not dealing with like the whole front end thing? I can say that I work in React all the time. But you don't necessarily need to. Some things don't need it. And template strings, when they were added to Node or when they were added to JavaScript, the language, were a great way to set up these really lightweight, simple templating languages. You can do the same thing in Reason. So here we have this special syntax of curly brace J pipe. And what that does is everything in between curly brace J pipe is treated like a string. And we have a special interpolation operator, $open parentheses, and anything inside $open parentheses is treated like a variable and interpolated into the string. So you can set up really simple HTML templates this way. So you don't actually necessarily need to add very much more to the language to build a full end-to-end HTML server. So all of the code that I've shown is available on GitHub. I've put my money where my mouth is, and it's actually powering the website that I use to host the talks that I end up giving. So if you want to check that out, it's all hosted on an Express server. It's running on Heroku. I'm not doing anything really special with it. It's just like a stock standard Express application. It's got examples of how to handle asynchronous Express routes, of how to handle synchronous Express routes, how to do templating, how to do all that kind of stuff. So there's a lot of stuff that you can kind of check out with that. And a couple of the things that I want to kind of like lead off with as we finish up is the web in a lot of ways kind of started with this. It started with jQuery, with things that are, well, it didn't start with jQuery. I can see Shaki glowering at me with that idea. But we have this concept in JavaScript, and a lot of it is in front end, but some of it is in back end of, we just kind of set up these big functions and these big statements, and they just kind of go. We don't really follow them. We don't really worry about them. They break. We go. We fix them. We write unit tests sometimes, but they're not really able to give us any assurance that what we've done is correct. And at some point in the last couple of years, we've started to see JavaScript code that looks more like this. Looks a little bit more like Java, putting the Java back in JavaScript. We have classes, we have extends, we set up these hierarchies. Classes are a very, very alternative way to actually add types to a program. They're a way of adding hierarchies, they're a way of adding relationships between properties and between elements. They don't give you any compile time guarantees. They just tell you that if you create a new instance of this class, you end up with these properties by default. You can't really tell much from that. But there's a lot of code that looks like this. I write code that looks like this if I don't get to use Flow. I end up writing React, or I end up writing things on the back end that kind of look like this. If I'm lucky, and for the people who use types, if they're lucky and the job that you're at lets you use Flow or TypeScript or something like that, you might end up writing something that looks like this. This is a generic function, a generic class for the effect type. And it's a way of tracking effects through a code base. The type doesn't matter. It's not like the important bit isn't the code on the screen, but it's the idea that you can absolutely express these things in your day job using Flow or using TypeScript. But the reality is that for a lot of us, whether it's for our jobs, whether it's for our coworkers, whether it's for us personally, we're not quite ready for this. Or we might not want to go down that path. We might not want or understand or be ready or be able to convince managers or coworkers to buy in to the idea of setting up something like Haskell for our day job, or PureScript or Elm. But there's so many places in between where you might be in a code base now and where you might want to go to. That a language like RESON is a great way to get yourself comfortable with typed functional programming, to get your team comfortable with typed functional programming, to show companies and managers and the world that this is valuable and this is important, and to have fun. Like, it is fun, it's enjoyable. It might just be me, but I can't assume too much. But I've been playing with it for months now, and it is, for the first time in a while, really, really enjoyable to play with that. You get so much fast feedback, which you don't get in a dynamic language, where you don't have to reload a browser to see whether something worked or not. You don't have to run nodemon with node in the background and have all of your unit tests reloading every time. The compiler kind of gives you that feedback quickly, and it gives you it intelligently. You don't really have to interpret too much. It interprets for you, and it tells you what went wrong.